Hi, in this video I'll show you how to plot a graph properly in the IB physics and what the expectations are. Alright, so first of all, let's recall how you do in maybe primary all the way up to middle school or in IGCSE. So the way that you do is, let's say you are performing a physics experiment, let's say it's Hooke's law, for example. So you all know that the formula behind Hooke's law is F equal to kx, all right, or negative if you want to, but it doesn't really matter here. So let's say you have set your independent variable to be the force, because that probably is something that you do with the mass hanging below the spring to extend it. And then what you do is use a ruler to measure. So this is the dependent variable for the extension. And therefore, according to our tradition, you put the independent variable on the x-axis. So I'll put F here and Newton here. And also for the dependent variable, which will be x, and probably in cm or millimeter, will be on y-axis. So of course, assuming you have done the experiment, you have collected the data, and also by learning from the previous video, you should know how to deduce or acknowledge the uncertainty of force and x, which is the length here, according to probably the ruler or the electronic balance, how to measure its weight, etc. So let's say your data is probably something like this. Okay, I just roughly give some data. Okay, so what you do is, you can see, I mean, the data kind of like fluctuate and wobble around like an imaginary straight line. So what you do probably when you are in previous years is to draw a straight line. So you probably would have a ruler to put on top of your graph paper, and what you do is you want to draw a straight line. Alright, so a straight line could be something like these. Let me try to make it thicker first, okay, just for you to see more easily. And so then you may kind of move around, like this is like the ruler or the line that you draw. Try to decide, oh, how I can draw better, or maybe try to adjust this so that we try to find the so-called lines of best fit. Okay, so I guess this is probably what you do. All right, you can try to think about how you would do if you were me in this situation. And you cannot satisfy all the points, obviously, because there probably will be some point, unless you somehow artificially make the data, there should be some point that cannot be collinear for all the data. So for example, like this one and this one, you can see they can't be on the same line. Even if I try really hard, there must be some point that are not exactly on the line. So the teachers in the past probably told you that, oh, then you can try to get the average trend, like probably having the same amounts of dots on the upper side and the lower side, etc. So this probably is the best of the line of best fit you can draw in the previous years. However, if you think about this, there could be a problem, because imagine if I try to have this data plot, okay, these data are all correct, let's say, but then if I pass this graph paper to say 100 people, would they draw the same line of best fit? That's the question, right? So how you interpret the data will be very important for the next steps, because when we do experiment, we don't actually are just interested in that particular point, but the overall trend, so that we can find the relationship to predict what will happen in the future when you have a certain force, how you can predict the distance. So some people may draw this line, and some people may draw slightly steeper or less steep. So there might be some variation which we cannot control, right? And that would be terrible, because we would like people to be more consistent when we are doing our work. Some people may even do something like ridiculously like this. Okay, obviously this is ridiculous, but then they're making, oh, then the point above the line, the point below the line are also the same. You can see 4 points here and 4 points here, right? Or as ridiculous as similarly like this, okay, with a vertical line, 4 points on the right, 4 points on the left. So obviously these would not be acceptable to represent the trend. And therefore now we introduce you a new system called the error bars. Alright, so let's put this line aside first, we'll use it later on. What you have to do to make the so-called error bars is, since you already now learned the idea of absolute uncertainty, then for all these data, when you collect them, you should also have uncertainties as well. No matter it is raw data, as simple as this experiment, then I guess f and x are both raw data, which you can have the absolute uncertainty. In case you have processed data, for example, like density, you cannot measure with a tool directly. You can use the propagation rule that we learned in the previous video to deduce its own uncertainty. So each data may have different uncertainty. That's perfectly fine. No matter what you can do is imagine these are the data and say this is 1, 2, 3, 4, 5, so on, 9, 10, and same for here 1, 2, 3, 4, 5, 6. Okay, for simplicity. So for each of the data, like here, I probably would know their absolute uncertainty. So in this case, for each data, then I can draw the range of each data, and this is the most important thing about the error bar. So for example, for the first data I draw, probably I know the y-axis, which is the extension. It has a 0.1 cm uncertainty. So for that, I can actually draw something like this, right? Like a bar or something, right? Like the letter of I, which show the range, how much it cover. Okay. So same for the others. Since I probably will be using the same ruler measuring it. Oh, sorry, this is not 0.1, this is 0.2, but let's say just say 0.2 then. Then every single point of them, you can then add such a bar, right, to indicate in terms of x, the y-axis, how much range could be acceptable. In case you are doing something like maybe a process data, you find out a certain particular data has a much bigger absolute uncertainty. That's actually fine. What you have to do is just follow the number that you have for absolute uncertainty. So let's say somehow for this data it has 0.5, for example. All right, then I can draw the uncertainty bar, the error bars much bigger. So that's surely something that you can justify using what you calculated earlier. So imagine you are doing your IA, you can also do it this way. So firstly, have your data table result, and you find the absolute uncertainty with justification, and then you move on to plot this graph. Same for horizontal. So maybe I will choose another color to show you more clearly. Then you will be able to find the force meter. Maybe it will tell you the uncertainty of it. So let's say it has a certain range as well. Let's say around 0.2 as well. So in this case, you'll be able to find the X error bar because it is horizontal, which is relevant to the force. So once again, I'm doing it now in a more casual way. If you are doing it on a piece of paper, you really have to take a look at each point correctly to match with the x and y axis. You can't just do it casually like me. Or when you're doing your IA, very likely you'll be using a software to use it. So either using the Google spreadsheet or the usually the Microsoft Excel. There are many tutorials which you can follow later on. So here I'm just focusing on how to do it primarily with a paper first. So once you did this, then you are pretty much good to go, because in this case now for each of the data, then you know the limitation of each data. That means the acceptable range of it. Notice that for each of these data point is not just a cross, okay? It is actually a rectangle. So what I mean is, if you look at, say, for this one, because this is bigger, so it's easier for me to explain. The data point doesn't just follow across these two lines, again across, but it actually also covers the whole area, because if you think about the worst case, then you may have the minimum of y and minimum of x that makes you to this point, or maximum of y and maximum of x, which makes you to this point. Same for the other. This would be minimum of x, maximum of y, and same for the other point. So that is to say, you can actually have the whole rectangle area that is being acceptable. Okay, so I'm going to erase this just to not confuse later on. So this applies for all the data point, and what I can do right now is, if you try to fit the line again, then there should be no one can now try to fool around, say, oh, I would like to use this trend line to represent because this is balance. There's no such thing called balance from now on, right? There's only one thing, that is whether the line pass through the error bar. If it doesn't, then either you can claim the line is wrong, or that particular point is an anomaly. Okay, so this line obviously is not going to be representable or valid, or of course this case as well. Right, this horizontal cannot be representing the trend. So the only thing that you can do is you can draw one straight line through all the error bar. Of course, the world is not perfect. Your experiment may go wrong. Rhyme, okay, and there might be, just might be, all right, a point that is somewhat below. Like there's no way you can fit a line if you think about like how you like to do it. Like you actually you can, but okay, let me just make it more exaggerated. Maybe, just maybe, you could have a point that is like right here. Okay, so obviously like there's no way you can draw a straight line that is through it. So what should you do in this case then? I guess you have to judge really based on your experience, based on what you can see, or you can redo the data near this point, and this obviously is an anomaly. Okay, you can either if you find out after repeating the experiment, find out, oh, this is actually not the case, or something went wrong for some reason, then you can probably ignore this point. Or if you don't have time to redo the experiment, then just keep it like this and just claim this one is the anomaly. Okay, so for simplicity, now I'll just ignore and erase it. So for the next steps, after you got the error bar, you have to think about this. When we try to draw a graph, what we care the most other than the relationship is to probably find out either the area or, more importantly, usually the slope. So if you think about the slope here, what does that mean in physics? I'll give you 5 seconds. The answer can be derived by looking at the x and y axis, because for the slope in mathematics it is delta y over delta x, and here physically it will actually be delta extension x over delta f, okay, or you call it rise over run in mathematics. So if you look at this and look at the original equation that we know, f equals to kx, and so you can rearrange the equation as in x over f equals to 1 over k. So that is to say the slope actually means 1 over k. K is a spring constant. So if you look at this graph that we did, it is not the best because within the error bar there's still space for you to kind of move around, and there's some sort of range you can find out. Ultimately, we want to use the graph and also, of course, all your data to find out the range of k probably. So how do we do? Let me give you another 5 seconds to think about it. The answer is simple. You just have to draw 2 more lines to show the worst scenario. That means the maximum and minimum. So here, let me try to do it with different colors. So let's say I use, say, the green color. Okay, let me just put aside the blue first. All right, because in fact, the original line, that is so-called the line of best fit, is not really that useful. But then anyway, so let me just try to find out the maximum slope first. So what you have to do is you really have to use a line. Since you know this is a linear line, by the way, then you can try to adjust by using your ruler again to see how you can obtain a straight line that is of course straight still, but then it passes through all the error bars while keeping the slope as large as possible. So while you're moving, one trick that you may want to do is by looking at the first data point and last data point. Once again, if you remember, it was having a rectangular shape, right, that is being acceptable. So let me use a gray color to kind of color it in so you can kind of see the range better. What you can do with it is, if you want to find the greatest slope, one way to check more quickly is by looking at the top left, okay, around here, top left of the last data point and the bottom right of the first data point. Yeah, that's correct. So in this case, okay, I'm not saying that you have to draw from that point to that point. You can actually draw longer. All right, and quite likely that's gonna be the greatest slope. But one thing that you should do is you should not take it for granted, because there might be a certain error bar that are not covering a large area enough. Then you may miss a certain point which you intend to cover. So this is just a way for you to check probably the quickest. So if I now try to check, yes, actually you can see this data point unfortunately is not covering it enough. So what I have to do right now is I probably would want to adjust slightly, because I really cannot justify this slope, so I have to compromise to have a bit more gentle one. So I guess this one would now be the best. Okay, so because now it's now touching this, and well, we cannot get the corner, but then I guess it's good enough. So this one will be called as the maximum line. So let me put the name here. So for green color is the maximum line, and obviously we are going to get the other one, which is called the minimum line. So let me copy this and change it to maybe a other color of yellow maybe. Okay, so similarly, if for the maximum line you can get that two corner to try to be the first step, then for yellow line it's gonna be the same. Let me give you 10 seconds to think about which two corner we should choose. Alright, the answer is obviously the top left of the first data point and the bottom right of the last data point. And of course, you can always draw longer than that, because this is more natural. Alright, to show that it's not just within those data points. So right now, let's again, this is only the first step to check the minimum line. It cannot always be the justified one, because you have to check once again whether or not those error bars will be covered by the line. So I think we are all good this time. Yeah, so let's just take this as the minimum line. So let me just write down here that it is called the minimum line, all right, for the yellow one. So finally, if you like to keep the line of best fit, that is of course, I mean, that is necessary actually, but then you don't see much of the meaning right now, because you cannot observe much quantitative idea from the blue line. How we should do instead to really get to know the range of the K or the slope is by looking at the slope of the green line and yellow line, which is the maximum and minimum line, and by calculating it we can then find the value. If you are doing it on the graph, then obviously you have to find the two coordinates, so probably this point and the other point that's probably here, to find the slope by using the 2-point form. Same for the green line. Because of the time, and I'm sure that you know how to do it, let me just skip that part and I'll just give you a fake number into it. Okay, so let's say you find out the slope of yellow and green, which give you the upper bound and the lower bound of the slope, which is once again 1/k. So let's say for the maximum one it would be 1.4, let's say, and for the yellow one it will actually be 0.8. Okay, I just make up the number. You can of course calculate it by using the coordinates. So what you mean in physics here would mean 1 over k has a limit from 1.4, actually you should include this as well, to 0.8. However, we are most intrigued by the value of k, but not 1 over k. So what you can do is simply use a bit of maths to find out the value of k, simply just calculating it. Alright, so in this case it will be 0.714, so I take it as 0.1, and also 1 divided 0.8, that's gonna be 1.2. So let's say this is 0.80, then I can take 1.3 then. Okay, so this is eventually what we care the most, right? We somehow manage to find out maybe for the spring constant of this one has a range of 0.71 and 1.3. And probably in your IA, you want to compare this value with the literature or other researchers' result. In a case where you may probably finding something like a, for example, gravitational acceleration of the Earth 9.81, then you can compare yours to see whether the 9.81 will fit within your range to justify your experiment also. There are two more important ideas that you have to understand before we end this video. The first thing is when we try to extend the line, there's one more thing you can check is whether or not your experiment has systematic error. Okay, so if you recall what we learned earlier, we have two kinds of errors. The one is random error, which can be shown by the error bars now on our graph, and whether or not our line is covering all the error bars or not. Because if you don't, that means maybe your random uncertainty or random error is underestimated or something goes wrong with that. However, for systematic error, what you can see is by using this approach and also extend your line slightly longer, of course without changing its slope, longer as in go over the origin. So right now, I think if you try to look closer to right here, alright, I assume if I do it properly and also the line is narrow enough, see if I can change it. Okay, I can change it. So I guess that applies as well if you're really doing a graph on a piece of paper with your pen and pencil. Then you want to keep your line thin as well, because that can tell you a more accurate situation. So right now, I hope you can see this thin line actually cover the origin. So what I mean is that if you are thinking about within the yellow line and the green line, right, this actually cover you a certain region, right? If I try to make it more visible once again, okay, and it actually cover a region that is saying from here to here. These are all valid data, all right, up to here, right? So all the color that I'm showing you right now in blue will be so-called the valid area. So that means the relationship could actually be acceptable and happen within this area. Of course, you don't have to color it, okay? Don't do that in the real graph paper of yours. But then I'm trying to show you, in this case, then this area will cover. The most important thing is it cover the origin as well, like just like what I showed you earlier when I zoom in. So I'm not going to do it again. So you know the origin is covered as well. In this case, then you can then claim your experiment doesn't have systematic error because of that. Because when we try to look at the original equation, f equal to kx, there is nothing behind. So that is no plus c or something behind. If you recall what you learned in mathematics for linear equation, it is y equal to mx plus c. So that plus c is the y-intercept, which set you off to somewhere else instead. Here, since we don't have that, that means the y-intercept is supposed to be 0, right? It's supposed to be 0. So f and x will have a proportional relationship. So in this case, since we cover that, then we can declare that there is no systematic error, which fits with our theory. Then you may ask me, so can you show me an example of when systematic error happened then? Then in this case, then what I may need to do is, let me just erase the color first. Then you would have probably, let's say the yellow line is somewhat steeper like this, all right, or according to the error bar. So I just forcefully make it. So let's say right now is what happened. So ignore what happened at the top, but right here you can see the only area that you can cover is only here. Okay, around here only. So you can clearly see that the origin is not being covered by this area. So that is to say, you must have a certain y-intercept that is non-zero in your relationship of your practical data. So that means there must be some systematic error. So if this happened in your IA, surely you should discuss it. You don't have to hide it. You should have pointed it out and discuss and try to think about what is the plausible, possible explanation of the source of systematic error. Lastly, one idea that I would want you to know is there are times where you may have the data that show more like a pattern like this. So obviously, you probably would not want to use a straight line to express a trend because this obviously is a curve. So when you are asked to draw the line or best fit, you could actually draw a curve. So that is to say, a curve that still pass through all the error bars. Of course, it should be a smooth line that you can draw, I guess, better than mine here. The other thing that you should pay attention in this case would then be you cannot draw max mean line with a curve, because for max mean line it only is applicable to a linear line only. There's no way you can talk about a curve's slope, because for a curve the slope is changing for each point, or you have to draw the tangent to each point to find a slope at that particular point only. So for a slope you cannot draw max mean line, and that is to say you cannot further deduce some physical meaning from it. So that's why in the later video I would introduce you an idea called linearization, and that is to say to put a curve to make it linearized, to make it straight in this case. So I would explain more in the future videos. Since this is a long video, I would like to make a small summary. So we talk about the error bars, how we can justify from your previous work, as in absolute uncertainty, you may need to propagate from what you learned earlier to draw the error bars for x and y axis. And then you try to use those error bars to draw the max mean line, which is the worst case, the greatest slope and the least slope. And then you can then find the range of the slope by interpreting the physical meaning of the slope. Then you can determine whether there are systematic errors as well. And lastly, some important idea about the curve. If you find this video useful, please click the like button and subscribe to my channel. You can also ask me any question in the comment section down below. I'll see you again next time.